Welcome back, everyone. This is Dr. Gounstein, and we are here again for lecture number 10. Okay, I'm very excited about today's lecture because today we are starting a new section of the class. So today we're starting this section where we're really going to dive in deep to trying to solve the problem of omitted variable bias. So far in the class we have seen that omitted variable bias is a major problem for us, and it's a major problem because it causes bias in the estimated coefficients in our model. And we alluded earlier to some ways of solving that, but in this section of the class, this new section that we're starting today at lecture 10, but we'll continue for several more lectures, is we will learn different tools or methods that we can use to try to solve that omitted variable bias problem. In lecture number 10, we're going to start the first and we could say the best way of solving it, and that is using randomization. Or put it another way, that is using a perfect experiment. So today we will learn how to use, in a certain sense, economic experiments to solve the problem of omitted variable bias. Okay, so that's what we're going to do today in lecture number 10, and we'll continue that same theme through future lectures. And with that, let's go ahead and begin. All right, so the biggest problems in econometrics is the omitted variable bias problem. So as economists, when we study data, we want to be able to observe unbiased relationships. We want to get an unbiased estimate of the true relationship between variables. And even more importantly, we often want to determine the causal relationship between variables. We want to know what effect X causes on Y. We want to know the causal impact of variables. Okay, so omitted variable bias makes our estimates inaccurate such that we can't trust our estimates to give us, to represent for us the true information about the relationship between variables. And so omitted variable bias is one of our biggest problems because it gives us, well, biased estimates. And with biased estimates, we can't we can't say that we can't conclude that we know the true relationship between variables, and we certainly cannot say that we have the causal relationship between variables. And so we're going to devote this lecture and future lectures to trying to solve this omitted variable bias problem. Okay, so let me first just do a little bit more review here of the omitted variable bias problem. So consider a generic multivariate regression model. So we see that here. We have our dependent variable y. In this particular example, I have three independent variables, x1, x2, and x3, with their corresponding coefficients. So let's say that we have this model and we are particularly concerned with identifying the effect that a change in x1, so x1 here, has on y. So that means we're particularly interested in knowing the relationship between x1 and y. That means we really want an unbiased estimate of beta 1. We want to know what beta 1 is. So we want an unbiased estimate of beta 1. All right, so let's say we're doing this analysis and what we really want the most is an unbiased estimate of beta 1. All right, so we want an unbiased estimate of beta 1. Our greatest concern is that there's likely to be omitted variable bias. So that is, there are likely to be other variables that are correlated with y and correlated with x1, which are omitted from the regression. In fact, there are likely to be variables that do not even exist in our data set, which are correlated with y and correlated with x1. And this means we're not going to be able to include them in the model. Without including these variables, we will have omitted variable bias. All right, making this a little bit more formal. Imagine that there's some variable z that does not exist in our data set. All right, there's some variable z, and it's not in our data set. We don't have it in our data set. So if there exists this variable z, it's not in our data set, so it's definitely not in our model. If there exists this variable z, and variable z is obviously omitted from the regression, okay? And if variable z is correlated with x1, all right, so there's some correlation between this omitted variable z and x1. So if there's some correlation between z and x1, all right, and there's some correlation between z and y, All right, so that means this omitted variable is correlated with, it's related to the dependent variable. All right, so if z is correlated with x1 and it's correlated with y, then there will be omitted variable bias. And there almost always is a z. There's always some variable that is not included in our model that is correlated with our variable of interest, so in this case x1, and correlated with our dependent variable, y. Okay? And so if there is such a variable, if there is a variable that is missing from your model, and that variable is related to or correlated with the dependent variable, and it is related to or correlated with the independent variable that you're interested in, that in this case x1, then the coefficient estimate on that variable, so in this case beta 1 hat, the estimate of beta 1, will be biased. And the question is, how do we solve that problem? How do we solve this omitted variable bias problem? All right, well, let's talk about one of those solutions today, and we'll talk about some other solutions in future lectures. All right, so the best way to solve the omitted variable bias problem is if we can randomize, if we can get random data. All right, what does it mean? What does that mean? Well, let's go into the details. All right, the best way to solve the omitted variable bias problem is randomization. All right, specifically, this means that the variable of interest, all right, in this case x1, is randomly determined or randomly assigned. So the variable is randomly determined or randomly assigned. All right. Okay, if x1 is randomly assigned, okay, and I'm going to talk a little bit more what do I mean by that in a minute, but suffice it to say for now, if x1 is randomly assigned, then x1 will not be correlated with any other variables. And if x1 is not correlated with other variables, then there will be no omitted variable bias for x1, for the beta on x1. So if x1 is randomly assigned, the correlation between some omitted variable, z, and x1 is 0, which means that there will be no omitted variable bias for the x1 coefficient estimate, even when z is excluded from the model. All right, so if x1 is randomly assigned, all right, then it's going to be uncorrelated with all the other variables, including variables that are missing from the model, including z, which is missing from the model. And if it's not correlated with z, then there will be no bias in our estimates of beta 1, even when z is excluded from the model. All right, so randomly assigning the variable of interest solves the omitted variable bias problem, because if it's randomly assigned, it's not correlated with the missing variable. It's not correlated with the missing variable. Remember, there are two conditions. There are two conditions that need to be met for there to be omitted variable bias. The omitted variable z needs to be correlated with your independent variable of interest, and the omitted variable z needs to be correlated with your dependent variable. All right? Those both conditions need to be true to have omitted variable bias. And what I'm saying is that if we randomly assign the treatment of the variable of interest, x1, then x1 and z will no longer be correlated with x1, in which case there will be no omitted variable bias for the estimate of beta 1. All right, so randomly assigning the variable of interest solves the omitted variable bias problem for the variable of interest. So then we can get an estimate of the coefficient on the variable of interest that would be unbiased. All right, so what does this mean? Let's take this and let's go deeper. All right, so talking more about randomization. What do I mean by random? So random information or random data is not correlated with any other information or data. Okay, so if it's random, it's not correlated with any other information or data. All right, so random assignment means that the values of the variable, so if a variable is randomly assigned, then the values of that variable are determined randomly. The values of the variable are determined randomly. So if a variable is randomly assigned, that means that the values of the variable are determined randomly. All right, there's a couple other words we can hear for this, so I'll talk about this more in detail. All right, if a variable is randomly assigned, we say that it is exogenous. It's exogenous. If it's not correlated with anything else in the model or in the system, then the variable is exogenous. All right, if a variable is not randomly assigned, if it's determined or related to other things in the model or excluded from the model, we say that it is endogenous. Let me make this more clear. So if a variable is randomly assigned, we say that it is exogenous. Exogenous means that the variable is not determined by or correlated with other variables. It is determined exogenously or from outside of the system that is being studied. All right, so using a Google definition, exogenous is relating to or developing from external factors. So if a variable is exogenous, that means it's not related to the things in the it's not related to the things in the system that you're studying. It's not related to the variables that you would want to include in your regression model. All right, so if a variable is randomly assigned, it will be exogenous. If a variable is not randomly assigned, we say that it is endogenous. So endogenous means that the variable is determined by, endogenous means that the variable is determined by or correlated with other variables. That means it's determined endogenously or from inside the system that is being studied. So using Google, this means having an internal cause or origin. So if a variable is endogenous, that it means it's related to, it's determined by, it's influenced by other factors that are in your model or factors that should be in your model. All right, it's related to other things. All right, I'm going to keep making this more clear as I keep going. Okay, so I've defined these terms. I've talked about randomization. Now let's go into more detail. What does it mean to randomly assign a variable? Okay, so I've already said that if your variable of interest is randomly assigned, then we will not have omitted variable bias. Because if it's randomly assigned, it's not going to be correlated with or determined by other variables in the model or other variables that should be in the model but are excluded. Okay, so, and then I went on to say that if a variable is randomly assigned, that means that its values are determined randomly. All right, so it's only by random that the values take any particular, that the variable take any particular values. All right, but now let's make this even more clear. What does it mean to randomly assign a variable? All right, this means that we appoint individuals in the data set to receive some intervention or not. All right, this intervention is the variable that we are interested in. This is the variable that we're interested in investigating. We typically call this the treatment or the intervention. Okay, the treatment or the intervention is some exogenous intervention into the economy or the decision-making process of economic agents. Okay. All right, so randomly assigned, that means we have some intervention, okay, and we are implementing it into the environment, into the economic environment or the decision-making environment of whatever economic agents we're studying in our analysis. All right. So examples of treatment. So let's say we want to know the impact of textbooks on students' test scores. So a treatment would be, or an intervention would be, will we provide some students with textbooks? The textbook is the treatment or the intervention. Let's say we want to know the impact of exercise on health outcomes. So then we provide individuals with some incentive to exercise. Let's say free gym memberships. Well, the free gym membership is the treatment. It's the intervention. And we want to look at the impact of this intervention on health outcomes. All right, so there's a couple examples of treatments or interventions. All right, so what does it mean to randomly assign a variable? So what this means is that we randomly determine who receives this intervention or this treatment. So imagine we have a sample of 500 students. We want to know the impact of textbooks on the students' test scores. So we randomly select 250 students and give them textbooks. The other 250 students do not receive textbooks. All right, so we take the sample of 500 students, and then we randomly pick 250 of them. We randomly pick 250 of them, and we give them textbooks, and then the other 250 do not receive textbooks. All right, so now whether or not a student owns a textbook is determined randomly. So whether or not a student owns a textbook is determined randomly in this case. It's not determined by anything else. It's only determined by random chance whether or not a student owns a textbook in this context, in this illustration. All right, so that's what it would look like to randomly assign a variable. The values of this variable, this ownership of a textbook variable, are determined randomly. All right, and so now there will be what we call a treatment group and a control group. The treatment group is the group of observations that receive the intervention. So in this textbook example, all of the students that receive a textbook are in the treatment group. And the control group is the group of observations that do not receive the intervention. Okay, so there's now a treatment group and a control group. The treatment group is the group of people that receive the treatment or the intervention. The control group is the group of people that do not receive the intervention. All right. So now imagine, let's keep going. Let's go into detail here. Now imagine that x1 was randomly assigned. All right. So we were using this example before. We have this generic regression model. We have this dependent variable y. We have these three independent variables, x1, x2, and x3. And we want to know what is we're particularly interested in the relationship between x1 and y. All right, so we're particularly interested in beta 1. All right, and now in this case, we're saying that x1 is randomly determined. It's randomly assigned. That means of all the people in our sample, we have randomly chosen some people to receive whatever x1 is, and other people to not receive it. All right, so now x1 is a binary variable that indicates whether or not an individual is in the control group or the treatment group. So now x1 is a binary variable. x1 equals 1 if a person is in the treatment group, and x1 equals 0 if they're in the control group. All right, and whether or not someone is in the treatment group or in the control group is randomly determined. We have randomly selected some group of people to receive the treatment and another group of people to receive the control. All right, so now x1 is random. All right, so then let's apply it to our example to make this more clear. So we want to know the relationship between individuals' test scores and their ownership of a textbook. All right, we want to know, does owning a textbook increase students' test scores? All right, so then imagine that we have this regression. All right, we are interested, so we're taking our generic model here and we're just making it specific to our example. The dependent variable is test scores, and now x1 is whether or not the student has a textbook. All right, so the dependent variable is test scores. All right, x1, the variable of interest, is ownership of a textbook. And now we're saying that if we randomly assign textbook, that will mean that there is a random subset of this sample population that will have a textbook. So text will equal 1 if they're in the treatment group, they receive a textbook. And text will equal 0 if they're in the control group or did not receive a textbook. All right, so that would be random assignment. We randomly determine who gets a textbook and who doesn't. Okay, now, so let's use this example. Using this example, let's say we want to know what is the impact of owning a textbook on students' test scores. So we are particularly interested in finding an unbiased estimate of beta 1. We really want to know beta 1. All right, so let's use this example. Now, I want to think about this example first from the perspective of not having a randomly assigned treatment, and then second from the perspective of having a randomly assigned treatment, just so we get a nice comparison of what randomization does. Okay, so here, this is our model. This is what we want to study. Here's our research question. We want to know, how do textbooks affect students' test scores? Okay, so we really want to know, what is beta 1? So we want to get an unbiased estimate of beta 1. Well, now, in that context, let's think about this when textbooks are not randomly assigned, and then let's think about it when they are randomly assigned. And we'll hopefully make this more clear. All right, so first, let's think about it without randomization. So let's say that we did not randomly assign people to receive textbooks, but instead, we just went into a population of people, population of students, and we just collected data. We just collected data on whatever the situation is, as of now. Okay, we just collected data on a population of students. Now, if we go in and we collect data on a population of students, we will find that some of the students have textbooks and other students don't have textbooks. All right, if we just go into some population of students, we collect data, we will find that some students own textbooks and other students do not own textbooks. In this case, if we just collect data, we don't randomly determine who has the textbook, but we just collect data. The ownership of a textbook, all right, this text variable, the ownership of the textbook will be an endogenous. That means that the ownership of the textbook would be correlated with numerous other factors. And we can imagine it. So let's just think about it. We go into a population of students and we collect a sample of data. We go and we ask a whole bunch of students, do you own a textbook? Okay, they say yes or no. And they tell us, and we ask them what their test scores are. Okay, and we ask them a bunch of other things, a bunch of other information. If we just go into some sample population of students and we ask them this information, I think that we'll find that students that own textbooks are going to be different than students that don't own textbooks. I think we'll find that whether or not a student owns textbooks will be highly correlated with whether or not, with what the student's income is or what the student's parents' income is. If a student's parents have very high income, they're probably much more likely to have a textbook. If the parents are low income, they're probably less likely to own a textbook. Okay, and let's imagine other things. So the students have access to other educational materials, other ways of learning other than textbooks, maybe the internet, for example. Those students might be less likely to own a textbook. We also might find that students that are particularly motivated or committed to their education, students who really love school and really want to flourish and do very well in school, those students are probably much more likely to own textbooks. All right, so the ownership of a textbook, if we just go in and collect data from a sample of people, we'll find that the textbook variable is endogenous. It's endogenous. It's determined by all kinds of other things. It's going to be determined by how much the student's income is and the student's level of commitment to education, students' access to a bookstore, all kinds of things. All right, so this textbook variable will be endogenous. It will be determined by things within the system. All right, so now the ownership of the textbook variable, so this is if we just go and collect data, it's not randomly assigned. We go in, collect data, the ownership of a textbook will be endogenous. So in this case, ownership of the textbooks would not be random. Textbook ownership would almost certainly be correlated with variables that are excluded from the model. This would result in omitted variable bias. All right, so we can imagine that there's probably some variable z that is missing from the regression model that is correlated with ownership of a textbook and correlated with test scores. Almost certainly there will be some variable that is not in the model, some variable that we don't have data on, some variable we didn't collect data on, that will be correlated with ownership of a textbook and correlated with the test scores. I gave a couple examples of some variables here. I think we can think about that. So here are three variables, three things that might affect whether or not a student owns a textbook. The student's income will affect whether or not the student owns a textbook. Now, we might have data on that. That's probably highly likely to have data on students' incomes or their parents' incomes. But let's imagine, but how about this third one? A student's level of commitment to education. A student who's really committed to their education is probably much more likely to own a textbook. So there's probably going to be a high level of correlation between the student's level of commitment and their ownership of a textbook. However, we probably don't have data on the student's level of commitment to their education. That would be a pretty tough thing to measure. It'd be a pretty tough thing to measure how committed students are to their education. And so that means we probably don't have data on the student's level of commitment, and therefore the student's level of commitment is going to be excluded from the model. It will be an omitted variable. But now I just said that student's level of commitment is correlated with ownership of a textbook. That means it could cause omitted variable bias. Remember, omitted variable bias is when we omit a variable, and that variable is correlated with our independent variable of interest and correlated with the outcome variable, or the dependent variable. So now the question is, if we have omitted the student's commitment to their education, if we've omitted that from the regression, will that cause omitted variable bias? Well, commitment to their education is going to be correlated with whether or not they own a textbook. Students that are highly committed will probably do whatever it takes to own a textbook. Will level of commitment also affect their test scores? Almost certainly. Students that are more committed will probably study harder, they'll work harder, and so they're probably going to be much more likely to do better on their tests. Therefore, a student's level of commitment to their education is correlated with textbook, it's correlated with test scores, and therefore, and it's omitted, so therefore we'll have omitted variable bias. All right, so that is the consequence of having an independent variable of interest that is not randomly assigned, or that is endogenous. The variable is determined by things in the model. Okay, so now that's without randomization. Now let's contrast this. Let's say that it is randomized. All right, so alternatively, let's say that we found a population of students that did not, or none of the students owned textbooks beforehand. Okay? And then we randomly selected students from this population and we gave them textbooks. Under that scenario, ownership of a textbook would be random. Ownership of a textbook would be random. It would not be determined by other things. It wouldn't matter how much their parents' income is. It wouldn't matter how committed they were to their education. It wouldn't matter whether or not they had access to other educational materials. It wouldn't matter at all. None of those other things would matter because it's not determined by any of those things. It's determined randomly. Okay, so now the variable of interest, ownership of a textbook, now the variable of interest, ownership of a textbook, is being assigned randomly. It's randomly determined who owns a textbook and who doesn't, which means now there's no other factor that is determining whether or not someone owns a textbook. It's determined purely by chance. Okay, so if we randomly assign who owns a textbook and who does not, then textbook ownership will not be correlated with other variables, including omitted variables. Okay, it's not correlated with other variables because the ownership of the textbook is not determined by anything else. Like I said before, it doesn't matter the age, the gender, the income level, the level of commitment. None of these things affect whether or not someone owns a textbook. The only thing that determined it was just the random assignment. And like I said, random information isn't correlated with anything else. It's not determined by anything else. And so now our textbook variable, Remember, text equals 1 if they own a textbook. It equals 0 if they don't. Now this textbook variable is not going to be correlated with the other independent variables, x2 or x3. And it's not going to be correlated with omitted variables. So even if we have omitted variables, like z, we have some variable z that's omitted from the regression model. Even if there's a variable that's omitted from the regression model, like variable z, there will not be omitted variable bias because textbook will not be correlated with z. And so therefore, if we've randomly assigned who receives the textbook, then we will be able to get an unbiased estimate of beta 1. We'll run our regression model and we'll get an unbiased estimate of beta 1 if the textbook variable is random. Because now the textbook variable is not correlated with anything else, including not correlated with z, the omitted variable, which means there will not be omitted variable bias. Okay, now at this point I want to make another thing extra clear here. So looking at this regression model, we have textbook as an independent variable. That's the variable we're most interested in. We also have x2 and x3 as independent variables. Now, if I randomly assign who receives a textbook, then I will get an unbiased estimate of beta 1. This does not, however, affect my estimates for beta 2 or beta 3. So beta 2 and beta 3 still might have omitted variable bias. The randomization only helps for the variable that has been randomized. If I wanted to know whether or not beta 2 and beta 3 were biased, I would have to do the same thing that I normally do, and that is see if there's any variables that are omitted from the model that are correlated with x2 and correlated with the dependent variable scores. Okay, so randomizing textbook does not make beta 2 hat or beta 3 hat unbiased. It only makes beta 1 hat unbiased. All right, so randomly assigning the textbook ownership does not solve the omitted variable bias problem for other variables in the regression model. Okay, so now that's randomization. When we as economists use randomization, we are performing an experiment. So when we randomly assign a variable, we call this an economic experiment or just a social science experiment. So these experiments are powerful tools for social scientists to study the effect or the relationship between variables. When we use experiments, the experiment allows us to determine an unbiased coefficient estimate. In fact, it even allows us to get a causal impact of the independent variable on the dependent variables. Okay, so let's make this more clear. So in our example of textbooks, the textbook is a treatment or an intervention. All right, we want to know the impact of this intervention, textbook, on students' school performance, on their test scores. Okay, if we randomly assign what students have a textbook, then we can determine an unbiased estimate of the relationship between test scores and textbook ownership. We can identify an unbiased relationship between ownership of a textbook and students' test scores. Okay, but now we can go even a step further. If we've randomly assigned the textbook, we actually are able to conclude that beta 1 is the causal relationship. That means if I get an unbiased estimate of beta 1, I can actually say that beta 1 is the causal impact of textbooks on test scores. I can say that textbooks can increase test scores by beta 1. Okay, so this actually allows me to get a causal impact. All right, so if we have our regression model and we've randomly assigned the textbook, we can estimate this model using OLS, a normal OLS model. We'll estimate the coefficients on the independent variables. We're most interested in the coefficient on the textbook variable because we want to identify the impact of textbooks on test scores. So we will find beta 1 hat, which is an unbiased estimate of beta 1. All right. So we will then interpret beta 1 as follows. We'll say textbooks cause students' test scores to increase by beta 1 hat. We have another term for this beta 1 hat, this unbiased estimate of the impact of test scores of textbooks on test scores. We call beta 1 hat the average treatment effect on the treated, or the ATT, the average treatment effect on the treated. It is the effect that the treatment variable has on the treatment group. It's the effect that the treatment has, the intervention, on whatever variable that on whatever outcome or dependent variable that we're interested in looking at. All right, so in this case, we wanted to know what's the impact of textbooks on test scores. We've been able to get that, the unbiased impact of textbooks on test scores. And we can call that the average treatment effect on the treated. Okay, now, so we've done that. I've drilled it into your head that we use randomization to get unbiased treatment effects or unbiased relationships, and that those relationships are actually causal relationships. All right, but now, even when we randomize, there are, in fact, ways in which we can get biased results. So there are still biases even in experiments. All right, so I want to talk about two examples of how we can still have bias even when we randomize, all right, so that we can know how to check for that and control for it. All right, so now I want to look at what are some biases that can arise even when we randomly assign an intervention, even when we run an experiment. Okay, so let's check it out. I'm going to go through two examples. There's more than this, but just in this course, I'm going to go through two. Two possible sources of bias that can come up when we do these experiments. One is what I'm going to call imperfect randomization, and the other is what I'm going to call imperfect compliance. All right, there are other examples, but I'm just going to go through these two in this class. Okay, so first let's do imperfect randomization. So randomization solves the omitted variable bias problem only if the random assignment truly achieves what we call statistical independence. Okay. Statistical independence is when the treatment variable, so the randomly assigned variable, so when the treatment variable is not correlated with any other variable. We could put it differently. If the treatment group is the same as the control group on average, then we have statistical independence. Or if we say the treatment variable is not correlated with any other variable, then we have statistical independence. Now, random assignment of the treatment should achieve statistical independence. That means if we randomly assign who gets the treatment and who gets the control, that should give us the statistical independence. The problem is that this really only happens if our sample size is large enough. And it's really hard to say how large. But if the sample size is large enough, then randomization will achieve the statistical independence. Randomly assigning who gets the treatment and who gets control will result in the treatment assignment being uncorrelated with other variables. However, if the sample size is too small, that means there are too few observations in your data set, then randomization may not actually achieve statistical independence. That means if the sample size isn't big enough, even when you randomly assign the treatment, it's possible that your treatment variable will still be correlated with other variables. And if that's the case, that can cause omitted variable bias if you omit some of those variables. All right, so basically, even when we randomize, our randomization can be imperfect. All right, and that's what this imperfect randomization is. So now the question is, if you've randomly assigned a treatment variable, you've randomly assigned a variable, you need to be able to know, you need to be able to check, test, you need to be able to see whether or not that randomization was we could say successful or perfect. Whether or not that randomization achieved statistical independence. You want to be able to see, is your treatment variable correlated with other variables? Another way of putting it is you want to see if your treatment group, the group of people assigned to your treatment, is the same as your control group on average. Okay. If your treatment group is the same as your control group on average, then the treatment variable is not going to be correlated with any other variable. All right. So if statistical independence is achieved, then we will not have omitted variable bias. All right. If statistical independence is not achieved, then we might still have omitted variable bias even though we randomized. All right, so we need to test for it. We need to look, we need to see, do we have evidence that we achieve statistical independence? All right, so if statistical independence is achieved, then the sample that received the treatment, aka the treatment group, all right, the sample that received the treatment should be the same as the sample that did not receive the treatment, aka the control group, on average in the absence of the treatment. So basically, you need to compare the group of people that you assigned to receive the treatment. You need to compare those people to the group of people that you assigned to the control. And you need to see if these two groups of people are the same on average. If they are the same on average, then the treatment variable will not be correlated with any other variable. Your treatment group is the same as your control group on average. In that case, you will have evidence of statistical independence. Okay. All right, so that's what we need to do. We need to test. We need to look. Is our treatment group the same as our control group on average? If it is, that's strong evidence of statistical independence. If they're not, then we don't have evidence of statistical independence and we have imperfect randomization. Okay, now this procedure, this test for statistical independence, we call this procedure testing for balance. All right, here balance means that the average value of a variable is equal between the treatment group and the control group. All right, so we perform a test for balance. We see whether or not the treatment group is the same as the control group on average. This is how we do it. So below you can see a typical, quote, balancing table. This is the way that we check for the statistical independence. What we do is we take a bunch of variables in the data set. Okay? And we calculate the average value for those variables for the treatment group and the average value for those variables for the control group. All right, so here in this example, I have our variables in the data set, so characteristics of the sample population. Here in this data set, we have parents' income, parents' land holdings, parents' education level, age, gender, distance. All right, so now here, we're still thinking back, we're thinking back to this question about textbooks and students' test scores. Okay, and so now we've divided our students into a treatment group, the group of students that will receive the textbook, and a control group, the group of students that does not receive a textbook. All right? And so of the students that will receive a textbook, we take the average of all these variables. Average parents' income, average parents' land holdings, average education level of the parents, average age, average gender, average distance to school. Okay, so we find these averages for the treatment group, and then we do the same thing, find the average for the control group. All right, and then we calculate the distance between these averages. All right, so here's the difference between parents' income, between the treatment group and the control. Here's the difference between parents' land holdings, between the treatment group and the control, etc. So here are the differences. So you can see what we're doing here is we're comparing the treatment group, the group of people that receive the treatment. We're comparing the treatment group to the control group. We're comparing these two groups of people. The treatment group, all the people that are going to receive the textbook, and we're comparing them to the control group, all the people that don't receive the textbook. So we're comparing these two populations, and we want to see, are these two populations the same or are they different? If the two populations are the same on average, that is evidence of statistical independence. That is evidence that we are able to identify an unbiased treatment effect. That is evidence that we will not have omitted variable bias. If the treatment group and the control group are not the same, that would suggest that we do not have statistical independence, which means we still might have omitted variable bias in our regression. All right, so we're performing this test. We calculate the averages and we find the difference. We do this for as many variables as possible. All right, all kinds of variables. All right, now then we look at the difference and we use a t-test to determine if the difference between the treatment group and the control group is statistically significant. All right, so we use a t-test to see whether or not this difference that we observe is statistically significant. If the differences are not statistically significant, then we conclude that there's no difference between the treatment group and the control group. Remember, if there's no differences between the treatment group and the control group, that means that provides evidence for statistical independence. That means the treatment variable is not going to be correlated with other variables. That implies that we will not have omitted variable bias for the treatment variable. Okay, so then we want to see, are there differences between these variables? We want to see, are there statistically significant differences between the treatment group and the control group on average? And so we use the t-test to look for statistically significant differences. We want to find no statistically significant differences, because that would suggest that the treatment group is the same as the control group on average, which would be evidence of statistical independence. All right. So if our sample size is big enough, all right, then randomization would imply that there are going to be no differences between the treatment group and the control group. That means we would see that the differences are not statistically significant. All right, now in this case, we indicate statistical significance with stars. All right, 3 stars means it's significant at the 1% level. All right, the significance is determined by mean t-tests. In this case, if we look at this case, we can see that 1 out of 6 variables is statistically significant at the 1% level. This would suggest to us that our treatment group and our control group are different. They are different on average. They're not the same on average, which would be evidence against statistical independence. This would mean we would look at this and we'd say, okay, our randomization did not achieve the statistical independence. That means we might still have omitted variable bias. All right, now let's go into more detail. All right, so we use balancing tests to validate the randomization. We use balancing tests to validate that the randomization did achieve statistical independence. All right, so this is to provide evidence of statistical independence. If the differences in the averages for a variable is not, if the difference in averages for a variable is not statistically significant, this implies that the treatment and control groups are the same on average for that variable. If enough variables show no average difference between the treatment group and control group, then we take that as strong evidence that our randomization achieves statistical independence. If we have statistical independence, that would mean that we will not have omitted variable bias for our treatment variable. That means we're going to be able to identify the causal impact of the treatment variable. Okay, now in practice, we balance across as many variables as possible. We perform the mean t-test for as many variables as possible. We do this for as many variables as possible, / as many variables as are appropriate, and I'll explain that more later. The more variables have no average differences between the treatment group and the control group, the more evidence that we have for statistical independence. All right, remember, I just want to make this very clear. If we have statistical independence, then we will not have omitted variable bias. Statistical independence means that the treatment variable is not going to be correlated with other variables, which means we will not have omitted variable bias. Okay, this balancing test is a test to see whether or not we have statistical independence. If we don't see differences between the treatment group and the control group, that means that if there are no differences between the treatment group and the control group, that means that we have statistical independence, which means that our treatment variable is not going to be correlated with other variables, which means that we will not have omitted variable bias. All right. Now, so typically in practice, if we're actually going to do one of these experiments, we will typically balance on a lot of variables. So we'll do this test, this balancing test for 15, 20 variables, a lot of variables. All right, and we have a kind of a standard threshold for determining if a sample is well balanced or not, or determining if we have that statistical independence or not. All right, and the threshold is this. All right, basically first we observe that, we just acknowledge that just by chance 10% of variables will be statistically significant at a 10% level, just by chance. So that means if you do your balancing test, if more than 10% of the variables are statistically significant at a 10% level, then the sample is not well balanced. That means we do not have evidence of statistical independence. Or we could say if 10% of the variables are significant at more than the 10% level, that would be evidence against statistical independence. Here's a really quick and easy way to think about it. If you do a balancing test, so let's say here's your balancing test. You produce your balancing table like this, where you have the treatment averages and the control averages, and then the differences. Here's the simple way to think about it. Here's your threshold. You're allowed to have 1 star for every 10 variables. If you have 1 star for every 10 variables, then you're okay. You have statistical independence. If you have more than 1 star for every 10 variables, that would imply that you don't have strong evidence of statistical independence. Okay, now a star, so every star is worth a level of significance, right? So if I have a variable and it has only 1 star, that means it's significant at the 10% level. If it has 2 stars, it's significant at the 5% level. If it has 3 stars, it's significant at the 1% level. And what I'm saying is this: you're allowed 1 star for every 10 variables. Okay. All right, balancing ex ante. Now I want to make a distinction here, and this is subtle, but it's important. We can conduct randomization. All right, we can do this balancing test, this test for statistical independence. We can do this before we conduct an experiment or after an experiment has been conducted. We can do it before the intervention has been put into place. So, using our example, before we give out textbooks, or we can do it after we've given out textbooks. And it makes a difference. If we do the test before we give out the textbooks, or we do the balancing test after we give out the textbooks, that is going to have an impact on how we do the balancing test, okay? So I'm going to make a distinction. I'm going to make a distinction between what I call ex ante. That means doing this test ex ante, before. Ex ante means before. So when I say doing a balancing test ex ante, I mean doing the balancing test before the intervention, and then doing the balancing test ex post. That means after the intervention. All right. So I want to make this distinction. So in general, we oftentimes balance before we implement the intervention. That means before we actually give it out. That means we collect data on a sample of students, and then we randomly assign some students to get the textbooks and some students not. And then we balance to make sure our treatment group is the same as our control group on average. We make sure that that's the case. We do our balancing test, and then we give out the textbooks. That's common. That's common practice. All right, if we're doing a balancing test ex ante, that means before we've given out the intervention, then we perform the balance test on as many variables as we can. And it's particularly important that we include the outcome variable that we intend to use in our analysis. So in the case of our example, the outcome variable will be student test scores. So if we're doing the balancing test before the intervention has been implemented, then we're going to do the balancing test on as many variables as possible. And we need to include the outcome variable. All right, if we're doing the balancing test ex post, that means after the intervention has been put into place, then we need to do the balancing test differently. If we're doing it ex post, that means we're doing the balancing test to be sure that the intervention, that when it was implemented, that it was truly random. If we're doing the balancing test ex post, then we can only perform the balancing test on variables that we can safely assume were not impacted by the treatment, by the intervention. We must exclude the outcome variable in this case. We must exclude any variable that we reasonably think could have been affected by the intervention, by the treatment. Okay. All right. So, solving imperfect randomization. All right. So, if we want to solve imperfect randomization, so the first thing that we do is we need to test for balance. We need to see whether or not we have perfect or imperfect randomization. If our randomization is imperfect, and we don't have an opportunity to redo it, if our randomization is imperfect, the first thing we need to do is acknowledge that the randomization did not achieve statistical independence. We have to acknowledge that when we report our results. And therefore, we have to acknowledge the fact that we can't rule out that there could be some omitted variable bias. The next thing we need to do is we need to include the variables that didn't balance in our regression. So it means if we do our balancing test and we found that some variables didn't balance, so if we go back to our example here, we found that distance to school was not the same between the treatment group and the control group. The treatment group was not the same as the control group on average with respect to the distance to school. Well, that would mean that I need to include distance to school in my regression. All right, so we need to include the unbalanced variables as independent variables in the regression model. All right, and the last thing we would do if we have imperfect randomization is we would consider using some of the other approaches that we will discuss later in the course. All right, now, the other problem, the other potential source of bias, imperfect compliance. All right, imperfect compliance. All right, now, what is imperfect compliance? Imperfect compliance is when we have randomly assigned people to receive the treatment and randomly assigned people to not receive the treatment, but not everyone who was assigned to receive the treatment actually got the treatment. Or not everyone that was assigned to the treatment actually used the treatment. Likewise, imperfect compliance is when some people who were assigned to the control group, they somehow got the treatment. So using our example, in our example, we're talking about the impact of textbooks on test scores. All right, and we've randomly assigned some students to receive textbooks and other students to not receive textbooks. All right, so the students that are assigned to receive textbooks, they're the treatment group, and the students that have been assigned to not receive textbooks, that's the control group. But now, what happens if some of the students that were assigned to receive a textbook don't receive a textbook? And what happens if some of the students that were not assigned to receive a textbook, so our control students, somehow they did receive a textbook? Somehow they gained access to a textbook. This would be called imperfect compliance, and this can create a problem for our analysis. Okay, so let's go into detail. So now let's define the following. I'm going to define two variables. I'm going to define a variable a and a variable t. The variable a will equal 1 if an individual is assigned to the treatment group. That means they're assigned to receive the treatment. And a will equal 0 if they are assigned to the control group. All right. But now, with imperfect compliance, not everyone who's assigned to the treatment group actually receives or actually uses the treatment. And likewise, some people that were assigned to the control group are able to receive or use the treatment. All right, so I'm going to find this other variable, t. Now t is going to equal 1 if the person actually received or used the treatment, and t will equal 0 if they did not receive or did not use the treatment. All right, so we can lay this out. There's 4 possible scenarios. It's possible that a person could be assigned to the treatment. That means they're supposed to receive a textbook, and they actually do receive a textbook. That person would be in compliance with the experiment. It's also possible that someone could be assigned to the treatment. That means they're supposed to get a textbook, but for some reason they don't get a textbook. So in this case, they do not receive the treatment. In that case, there would be an error. There would be imperfect compliance. There are people that are supposed to receive the textbook that did not receive the textbook. It's imperfect compliance. Likewise, we have people that are assigned to the control. So a equals 0. Now, if you're assigned to the control and you do not receive the treatment, that means you're assigned to the control, that means a equals 0. And you did not receive the treatment, that means t equals 0. That person would be in compliance. All right? They're assigned to the control, they're not supposed to get a textbook, and they didn't get a textbook. They would be compliance. However, you could have people that are assigned to the control, that means a equals 0, who somehow receive the treatment, that means t equals 1. That would be non-compliance. They're assigned to the control group, but they still get the treatment. All right? So the fact that these two things can exist, that means you can have someone assigned to the control but still get the treatment, or you could have someone assigned to the treatment but doesn't get the treatment. That means there's imperfect compliance. Okay. So now when there's imperfect compliance, I have 2 variables. I have this a variable, which is random. It's determined randomly. All right. The a variable is determined randomly. That means a equals 1 if they've been randomly assigned to the treatment group, and a equals 0 if they've been randomly assigned to the control group. All right. And I also have t. And t tells me whether or not they actually received or actually used the intervention. T is not randomly assigned. T is not randomly assigned. There's some people that were assigned to the treatment group but didn't get it. Some people are assigned to the control and they did get it. All right, so T is not randomly assigned. A is randomly assigned, but T is not. So now the question is, what do we do now? Up until now in this lecture, I said that if a variable is randomly assigned, then it will give us an unbiased treatment effect. The problem is that in this case, if there's imperfect compliance, then just being assigned to the treatment group doesn't mean you actually get it. So then what do we do now? If we want to know the impact of textbooks on test scores, if we want to know the impact of our treatment on the dependent variable, what independent variable do we use? Do we run a regression that uses A as our independent variable, or do we run a regression that uses T? If we run this second regression, let's say we ran the second regression and we use T as our independent variable. We know from the discussion on this page that that t is not randomly assigned. Okay, so if we run this regression, we'll get an estimate of the relationship between t and the dependent variable. We'll get an estimate of the relationship between the treatment, let's say textbooks, and test scores. The relationship between the treatment variable and y. Okay, we'll get an estimate of alpha 1. So this alpha 1 hat, we'll get an estimate of it. But we know that it will be biased because the treatment variable is not randomly assigned. It will have omitted variable bias. Okay, so that's not a good option. We shouldn't use that variable. But what about A? A was randomly assigned. Should we use that? If we run this regression, we will get an estimate for beta 1. We'll get beta 1 hat. It'll be an estimate of the relationship between having the treatment and y. But the problem is that beta 1 hat will be biased too, because some people in the treatment group didn't receive the treatment. And some people in the control group did receive the treatment. And so either way, we're going to have bias. So if we have imperfect compliance, our estimate of our treatment effect will still be biased. So then what do? Which one do we use? Which one do we use? Both are going to give us biased results. Both of them are going to give us biased estimates. Well, let's dig into the detail a little bit more on this beta 1. All right. So A is randomly assigned. All right. T is not. Whether or not someone actually received the treatment is not randomly assigned. Only whether or not they've been assigned to receive the treatment. All right. So A is randomly assigned. T is not. All right. So let's talk about beta 1. Estimate of beta 1. Some people in the treatment group did not receive the treatment. Therefore, the average outcome variable for the treatment group, so that means when A equals 1, the average outcome variable when A equals 1 will be smaller than it would be if everyone got the treatment. All right. Also, some people in the control group did get the treatment. Therefore, the average outcome variable, the average outcome value for the control group will be larger than it would be if not everyone had received the treatment. All right, so what does this mean? What's this imply? All right, so what would happen if we had this situation is that we would use A. We would use the first regression. That means even if we have imperfect compliance, we will still use our randomized treatment assignment as our independent variable. So when our experiment has imperfect compliance, we still use the variable that indicates the treatment assignment, which is A. We do not use the variable that indicates actual reception or use of the treatment. We do not use T, we use A. When we have imperfect compliance, our coefficient estimate, so the coefficient estimate we get from this regression, is just called something different. It's called the ITT instead of the ATT. ITT is the intent to treat effect. So basically, we run this regression model, and we get beta 1 hat, but instead of calling beta 1 hat the ATT, we call it the ITT, or the intent to treat effect. And the ITT is an underestimate of the ATT. Basically, beta 1 hat will be downward biased. Beta 1 hat will be downward biased. It will be smaller than the true impact of the treatment on the outcome variable. It will be smaller than the true impact. It will be downward biased. That means it will be an underestimate. It will be an underestimate. And we're okay with that. We're okay with getting an underestimate. All right, so if we ran this regression, we get beta 1 hat. We call beta 1 hat the intent to treat effect, or the ITT. This is a downward biased estimate of the true causal impact of textbooks on students' test scores. All right, so summarizing. If we have imperfect compliance, we still use the randomly assigned treatment variable. We use the randomly assigned variable. The variable that indicates whether or not someone has been randomly assigned to receive the treatment or not. We run that regression. We use OLS, standard regression model. We get our coefficient estimate, beta 1. We know that beta 1 will be biased. It'll be biased, but it'll be downward biased. It'll be smaller than the true causal impact. So it will be a downward biased estimate of the true impact, the true causal impact of the treatment on Y. So if we're using our textbook example, it would be a downward biased estimate, an underestimate of the causal effect of textbooks on test scores. So if I ran this regression, I would interpret it as this. I would interpret it this way. Textbooks increase students' test scores by at least beta 1 hat. Because it's an underestimate, it's the bottom. It's smaller than it should be. So it's an underestimate. So I can say that textbooks increase students' test scores by at least beta 1 hat. Okay, so let's do this in Stata to reinforce everything we just went over. Okay, so now in this demo, I'm going to use the data set called wages random. All right, wages random. I'm going to use that data set, wages random, so you can find that. All right, so in this data set, I have a couple things. All right, so now let's create my lecture. So lecture 12, perfect experiment. Perfect experiment. All right. All right, now, in this demo, we are looking at the impact of a training program on people's wages. All right, so we want to know if a training program on professional skills will increase people's wages. All right, so that's what we want to know. Now the training variable. All right, so first we're going to do two demos here. We're going to do two examples. Example 1 is impact of training with perfect compliance. All right, so the first one, compliance, we're going to illustrate using perfect compliance. And example 2 is imperfect compliance. Compliance. Okay. I'll read you two examples. All right, so now we want to know what is the impact of training. What is the impact of training in professional skills on people's wages? So this training program is, maybe teaching people how to give good presentations, giving people training on how to interact professionally, how to give a good handshake, how to interview well, how to, speak with confidence, things like that, soft skills, professional skills. Okay. So we're going to give a training on these soft skills, and we want to know how does this training impact wages? All right. Now we have been informed that this training program was randomly assigned. Okay, so that means we want to know what's the impact of this training program on wages. And so if we want to know that, we will randomly assign who receives the training and who doesn't. All right, so now in this data set, we've been told that this treatment variable has been randomly assigned. All right, and now let's do demo number 1. So perfect compliance. All right, so now in this example, we will use the variable treatment. Okay? Treatment. And this variable, okay, equals 1 if the person has been randomly assigned to receive the training. All right. And we will assume in this example that everyone that was assigned to receive the training did receive the training. Okay? Also, no one assigned to the control received the training. All right, so this means we have perfect compliance. All right. So in this example, perfect compliance. So now we want to know what's the impact of this training program, this randomly assigned training program, on wages. Okay, so we're going to do 2 steps. Step 1, test for statistical independence. All right, we want to know, was the randomization successful? Was the randomization successful? Did it achieve statistical independence? All right. So let's test for that. The way that we do that is we do these mean t-test comparisons. We compare variables between the treatment group and the control group. All right, so the way we do that, instead, we just do t-test, and we type in the variable. We type in the variable, and then comma, by, and then it's by the treatment. All right, so this treatment variable, we can tabulate it to see what it looks like. Treatment, all right, it's binary. It equals 1 if the person received the treatment. It equals 1 if they were assigned to get the training. It equals 0 if they were not assigned to get the training. And so now we want to know what is there any statistically significant difference between the group of people that were assigned to get the treatment and the group of people that were assigned to not get the treatment? All right. So we are looking to see if there are any statistically significant differences between the treatment group, so the treatment group is when treatment equals 1, and the control group. So that means when treatment equals 0. All right, that's what we want to know. Okay. If there are no differences, we should say no more than 10% of the variables significant at the 10% level. All right. So if there are no differences, then we have evidence of statistical independence. All right. So then let's do it. Now, this is a little bit tricky. So in this case, the training has already been implemented. The training has already been implemented. So this is ex post balancing. All right. That means that we cannot include variables that could have been affected by the intervention. All right, so now let's pick out variables that we don't think were impacted by the intervention. Now, wages. Do we think that wages could have been impacted by the intervention? Yes. Wages are probably affected by the intervention. So we don't include that. All right. What about the next one? Education. is the amount of education that a person has going to be affected by this training? No. All right. Now, measuring education, the number of years that they went to school. Okay. So no, this is not going to increase. So the training will not increase the number of years the person went to school. All right. So then education is a variable that we can use. Okay. What about experience? Is this training going to increase the number of years of experience that the person has? No. Is it going to affect their ethnicity? No. Is it going to affect their gender? No. No. Is it going to affect whether or not they're married? Hopefully not. No. Okay, so then we can include all of these variables. So let's do it. We're going to do a t-test for all these different variables. So let's just, oops. All right, education, experience, non-white, female, and married. Okay. All right. So now let's run these t-tests and let's take a look at what we see. So t-test education by treatment. So here's our results. So group, that is referring to the treatment. So it's referring to the treatment group. All right. So if the group equals 0, that means it's the control group. And if the group equals 1, that means it's the treatment group. All right, so the average number of years of education for the people in the control group is 12.6, and the average number of years of education for people in the treatment group is 12.5. The difference is 0.15, and we can find the significance here. So the p-value is 0.54. That is not statistically significant. So then there is no statistically significant difference between the treatment group and the control group on average. All right, so then let's do experience. All right, the average number of years of experience for the control group is 16.7. The average number of years for the treatment group is 17.3. The difference is 0.52. The p-value is 0.66, so it's statistically insignificant. There is no difference between the treatment group and the control group on average for experience. All right, let's do non-white. I'll just skim through this more quickly. All right, there's no difference between the treatment group and the control group. What about gender? No difference between the treatment group and the control group. Married? No difference between the treatment group and the control group. All right, so we've looked at all the variables in our data set, and we find no statistically significant difference between our treatment group and the control group. All right. Based on this analysis, we find we find evidence that we have statistical independence. So we will proceed with our regressions and believe that we will be able to identify the causal impact of the training on wages. There will not be omitted variable bias. All right, so that's the first step. We have to test to see if we have statistical independence. And then step 2 is our regression analysis. All right. So let's do it. Now, if the variable of interest is randomly assigned, then strictly speaking, we do not need covariates. So we can just do a simple model. Simple model is just reg, wage, treatment. Okay, so we can just run this model. Whoops. Let's open that up a little bit more. Okay, here we go. So here is our treatment effect. Here's our treatment effect. All right, it's actually statistically insignificant, which means that we would conclude that this is 0. And if we have no bias, then we'd say, okay, there is no effect of the treatment on wages. Okay, but now, even when a variable is randomized, all right, actually, let me make this clear. We do not need covariates. We can exclude other variables because we will not have omitted variable bias. All right. So, but we can still use a multivariate regression model. That means we can still include other variables. We might include other variables because including other variables can reduce our standard errors and increase the efficiency of our estimates. All right. Okay, so then let's take a look. So we can do reg, wage, treatment, and then we can include other variables. Education, experience, female. We can add a bunch of other variables. All right. So the standard error decreases when we add other variables. It decreases when we add other variables because our estimate gets more efficient. Now it's statistically significant. So here's our coefficient. All right. So we would interpret, so let's do it. Interpretation. The training increases, or let's say, all right. Wages increase. Here we go. I got it. Sorry. All right. The training program has a causal impact on wages of 0.56 per hour. All right. Another way to put it, I'm going to interpret this another way. The training program causes wages to increase by $0.56 per hour. Okay. All right, so that's the first example. Now let's do the second example, imperfect compliance. Now, just intuitively, we can imagine that just because an individual is assigned to receive the training does not mean that they will actually receive it. Maybe some people who were assigned to the treatment group, maybe some people that were assigned to the treatment group didn't attend the treatment, didn't attend the training. Also, maybe some people who were not assigned to the treatment group managed to be able to attend anyways. Okay. This would be imperfect compliance. All right. Now, if we're concerned about imperfect compliance, step one is to see whether or not we have it. So step one, check for imperfect compliance. All right. How do we check for imperfect compliance? Well, if we look at our data set, we have the treatment variable. All right. The treatment variable equals 1 if they were assigned to receive the training. And we also have this variable training. The training variable equals 1 if they actually received the training. Okay. So we have perfect compliance if training and treatment are the same. We have imperfect compliance if they aren't the same, if they are different. Now, one neat way that we can check for this, one neat way that we can present this and actually get an idea of how much imperfect compliance we have, if there is we just do tab treatment training. All right, this is going to give us a table. This is going to give us a table that shows us the number of people that are in the treatment group and the number of people that actually received it. So here on the y-axis, so we have the variable equals 1 if assigned to receive the training. All right, so it means this 0 means they were assigned to not receive the training, and this 1 means that they were assigned to receive the training. All right, and then over here we have equals 1 if they actually received the training. All right, so now this 0 means they did not receive the training, and this 1 means they actually did receive the training. So now we can look at all the 4 different cases. This is just like the lecture. This is just like this table. Assigned to receive the treatment, did receive the treatment, or assigned to receive the treatment and did not, etc. There's 4 possible cases, and this table is showing us. So what if you were assigned to the control group and you did not receive the treatment? All right, that would be correct. This would be complying with the treatment assignment. All right, so 251 people were assigned to the control group and did not receive the treatment. All right, this is good. Now, these are the people that are assigned to the control group but received the treatment. All right, so 1 here means received the treatment. So we come across here, we find 15 people were not supposed to get the intervention. They were assigned to the control group, but they got the treatment anyways. 15 people did not comply with the assignment, and they got the treatment anyways. Okay, now let's check here. 1, this column, all right, it equals 1 if they were assigned to receive the training. And then this 1 means they did receive the training. All right, so we look across here, 248 people complied. 248 people were assigned to get the treatment and did get the treatment. All right, now here, these people, again, the 1 means they were assigned to get the treatment. The 0 means they did not get it. And so now we see that there are 12 people. There are 12 people that were assigned to get the treatment. They were assigned to get the training. They were supposed to get the training, but they didn't get it. All right, there are 12 people that didn't comply. All right, so now we look at this table, we can say there is imperfect compliance. There are a total of 27 people that did not comply. All right, so by looking at that table, we can see that we have imperfect compliance. All right, so now step 2, check to see if the randomly assigned treatment variable, so in this case, treatment, actually did achieve statistical independence. All right, this is the same procedure as from example 1, so I will skip. All right. Step 3, run regression analysis. All right, step 3, run regression analysis. Okay, so now, in this case, we have imperfect compliance. We have imperfect compliance. We have imperfect compliance. So we know that there will be bias. All right, now the question is, do we use the training variable or the treatment variable? All right, training indicates if people actually received the treatment. The treatment variable indicates if people were randomly assigned. Which one do we use? Do we do reg, wage, treatment? Or do we do reg, wage, training? Okay. All right. We know from the lecture that we still use the randomly assigned variable. All right. So that means we do reg, wage, treatment. All right. So we run it again. Now we actually get the same results because I'm using the same variables, but we're just using it in a different context. All right, so we can do a simple regression or a multivariate, but we'll do with the multivariate. All right, so wage, so treatment, education, experience, female, whatever variables you want to include. We run the regression. Oops, I gotta shrink that. All right, but now we need to interpret it. Now we interpret. Okay, so 0.45, you know what? All right, so 0.56 is our ITT. Intent to treat effect. This is an underestimate of the true impact. The true impact of the training on wages. Okay, and this is how we would interpret it. I would say okay. The training causes, I'm going to emphasize this, at least, remember it's an underestimate, at least an increase of $0.56 per hour in wages. All right. So the training causes at least an increase of $0.56 per hour in wages. All right, because this is the intent to treat effect. It's an underestimate of the true impact. So this is because we have imperfect compliance. Because we have imperfect compliance, we will interpret the coefficients differently. Now in example 1, we assumed that there was no imperfect compliance. Okay, so we just said that the training program caused an increase of 0.56. So what we could say is so in example 1, when we assumed that there was no imperfect compliance, 0.56 was the, or I should say, is the ATT, an unbiased estimate of the true impact of the training on wages. But now when there is imperfect compliance, the ITT is, we get the ITT, which is an underestimate, which means we change the interpretation. We say the training causes at least an increase of $0.56 per hour in wages. Okay, thank you very much, and I hope that you enjoyed the lecture, and I will see you later.